first thing, the ideas of quantum teleportation, they started with the ideas of quantum information and quantum computation. So these things are kind of recent. If you think as math as something so old, and these things were born like quantum physics, like from Einstein's time, the beginning of 20th century, and only in 1993 we had the first ideas of quantum teleportation. So it's everything's so new. So there's so much to learn, but quantum teleportation is so beautiful, and I wish I was the person who found it, because it was like trying, guessing, and trying. I imagine that they got to it. So the idea of quantum teleportation is that if we have, for example, the dogs, Sonny that's in Michigan and Stormy that's in New Hampshire, if they want to transmit a quantum thing, a quantum bone, a quantum beat, or whatever, here's the quantum state they want to transport. And then I'm gonna draw the lines for a circuit. I try to do it as smooth as I can. Okay. So let's see. Here in qubit 0, I'm gonna have my state psi. That's the state the person or the dog in Michigan wants to transmit. And then dog 2 is gonna be here in New Hampshire, okay, to receive. So it's gonna be our Alice and Bob thing as we have in the examples. So, okay, we know that in order to teleportation happen, we need to have an entangled state, because having an entangled state, whenever I touch the state in my side, the state in the other side, the other bit of the state with the other person is going to be changed to, is going to be touched to. So let's call A and B or Alice and Bob just to correlate to the examples. So if Alice has this part of the information, she has this alpha and this psi state, that's alpha 0 plus beta 1. And she has a part Q1 of the entangled stage. She wants to send it to Bob. We will create then an entangled stage between A and B, or between Alice and Bob. Okay. And then I'm gonna try to make it very slowly and very, this part very well explained to make you understand the calculation. So our first part of the quantum circuit is drawn like that. Okay, we have Q2, Q1, Q0. But as we draw it, we know that Q2, Q1 are here, and they're together with psi, and we know psi. Okay, psi is, so I'm just rewriting. This is still Q0, but I'm replacing for psi. Okay. So I know also that with Q2, Q1, I can create an entangled state. So I'm going to create my bell pair doing these operations. And I know the outcome is going to be I'm using this bell pair here. Sorry, bell pair here. Still applying to my psi state, okay? Now, quantum teleportation means I'm gonna transfer the state that is in Q0 to the position Q1, having another thing in place of Q0. So in the end, I expect to have all this state here transposed to the other side. That's quantum teleportation. It's a mathematical thing. Now, I'm going to do some manipulation here. Okay, so we have the tensor product 0, 0. It's gonna operate in the other vector here, It's going to be another tensor product. It's going to be a triple tensor product. I'm just doing this operation here. And I'm putting alpha outside. Okay. So I'm just going to do this operation and then do some manipulation with it. So just following, oh, that's an awful plus sign. Do this decently. Oops, yes, correct, plus alpha. 0 plus 1. Okay. So now, and I'm copying from my previous calculation to not do anything wrong. Now I'm gonna apply a C0 gauge. Let me do it here. Because the next step of teleportation is applying a C0 gauge here. So I'm gonna apply a C0 gauge to this situation I have here. And the C0 has the control bit Q0. And the target's gonna be Q1. So for all of them, okay. Just to make it clear. So we are applying, this is gonna be control, this is gonna be target. So what we're gonna have here, this will not change because our qubit 0 here is 0, but the next one is gonna change. Is it correct? Yep. Then this is not gonna change. And the next one, Q1 is gonna change. Okay. And the next step for quantum teleportation is doing the Hadamard gauge here. I'm gonna add a barrier here. Okay, gonna use the next page to do. I'm gonna rewrite everything here after the C0, just to not lose. And now I'm applying the Hadamard gauge only to qubit 0. Okay. So qubit 0 is this one. I'm gonna put the constant for the Hadamard gauge outside to not have to keep repeating it. And this is the Hadamard gauge applied to qubit 0. I'm going to do for all the rest. Hadamard gauge on vector 1 gives rise to a minus sign. Oops, yeah, correct. Yeah. Now we have, I'm just multiplying here. So the amplitude of each factor here is gonna be 1/2, such such a way that the probability to find each of these things is 1/4. So I'm not changing the total probability of 1. And now what I'm gonna do, I'm gonna transfer this qubit here. I'm gonna operate this qubit on these things inside the parentheses and see what we get. Like when I transfer this inside, I need to keep the order. So it's 0, 0, 0, 1. I'm gonna do for all the rest. Zero, 0, minus 0, 1. Correct. Now it comes the beauty of the thing, and this is for me the most thrilling part. I'm gonna try to do it colors. I explained to my students morning, and I hope this is clear for you guys too. So I'm gonna use orange here first. Let's black first just to write the constant outside. I'm gonna use orange here to show. So I see a 0, 0 here, but also I see a 0, 0 here. And I see these factors outside. So I'm gonna factor them. Plus, I see a 0, 1 here, and also a 0, 1 here. So I'm gonna write them. It's minus beta 1, and it's 0, 1 here, plus this purple. I see 1, 0 here, and 1, 0 here, and these. Plus, I'm gonna do it pink now. The last one we have, it's 1, 1. So, 4, 1 plus minus, sorry. It's, 1 minus 0, 1, 1. So the state we wanted to transfer in the beginning was this one, psi. Psi was alpha 0, beta 1. And we want to read it. I'm sorry, it's gonna be messy here because as usual, I didn't leave much room. It's gonna be the registers, classical register 0 and classical register 1. I'm gonna measure what I have in position 0, and I'm gonna write it my classical bit 0. And I'm gonna measure what I have in qubit 1. In the end, this is Bob measuring. And I'm gonna read it in classical register 1. Okay, and then we'll see what happens. If Bob reads in the classical register. If he reads 0, 0, the classical register is C0, C1, okay? He needs to do nothing, applies identity, because it's already what he's reading. So fine, transpose the state. If in the classical register, remember we're reading Q0 in C0 and Q1 in C1. So for reading C0 in Q0 in C0, you're gonna reach 1, 0. We see the state is very similar, but it's wrong by one sign, one signal, a minus signal. And the matrix or the gauge that fixes it is Z. And if reads 0, 1, we see it's just flipped. We only need to apply a next matrix to fix it. And if it reads 1, 1, we need to flip the states and apply a minus signal. So we need to apply next gauge to flip the states and a Z gauge. So that's how we know which operations needed to be performed depending on the bit he's reading, depending on the classical bits he's reading. That's how I know if it's 0, 0, I apply identity. If it's 1, 0, I apply Z. 0, 1, I apply X, or 1, 1, I apply XZ. And that's the math behind this equation. Now, having done that, we know the drawing of the circuit, and we know what the circuit needs to do, because by many attempts, people got to this conclusion. That's how mathematically you can transpose a state from here to here, going from Q0 and taking position Q2. We know the shape of the circuit, and the homework this week was about building this in QxQ. So I'm gonna open mine here to show you guys. Let me just see if I'm sharing. Are you guys seeing my QxQ window? I have.
Yeah, Gisele, we can see it.
Okay, sorry, I just stopped sharing. I'm gonna reshare. I have the impression I'm not sharing it correctly, that I'm not sharing my QxQ. Now I am. So I don't know if I did all the operations correctly before, if you all guys saw this, because I don't know if I was sharing the correct screen, because I was doing these operations. So I had this in the other board too, but I hope you guys saw it. Okay, so I had the classical, and then 0, 0 identity, 1, 0, Z, 0, 1, X, 1, 1, XZ. And the homework was about building this circuit that I did. Okay, so yeah, let's follow it. I'm gonna try to zoom it a bit so you guys can see better. Yeah, I think I don't need to show anymore how to download and upload it here in QxQ. If someone still has some doubts in the other sections, I did it. So it's not hard. You just need to upload it in the Quantum experience and do the steps. So this is exciting because we're gonna build a circuit that does the teleportation, And we're gonna do it step by step as a function. We're gonna build a function out of several little functions to make it step by step and try to make it more obvious. So I'm gonna run this first cell here, and let's see. We need, for doing quantum teleportation, to create a quantum register and two classical registers, and we need to name them. So that's why we're doing it differently from doing it straight of we did last week, just like putting numbers here and assign quantities. We need to give names to our registers. So it's important to create as it's showing here. So we're gonna learn by repetition, by doing what people are teaching us to do. So we're gonna use these functions to build our circuit. So in the first step, the only thing I did here was copying from here and pasting it here, okay? And I know I will need 3 quantum registers because that's how we build our circuit. We need 3, and we need 2 classical registers that we're gonna name C1 and C1 and C0, but in this order, okay? C0, C1. And we are going just to practice here, the first step, just to measure. So applying the measure function here in this way is the same as applying in this way. We're gonna get the same result, okay? It means I'm measuring Q bit 0 in classical register 0 and Q bit 1 in classical register 1. But in the exercise, they ask us to do like that. It means I'm measuring 0 in 0 and 1 in 1. Okay, so it's the same. Okay, let's follow. So the next step is just an exercise to show the if gate. Okay, and it's showing us how to apply an if gate. So if I want to this circuit to apply an if gate in QxQ and read it in the classical register 0, and here in the command he put CR, but we named C0. So it's just a matter how you name it, just need to be consistent. It's just an example. You know the names you gave, the variables you're using, so you just correct it for the names you're using, just make it consistent. But here it's asking us to make it read in C1, not C0. So the only thing we need to do is copy the command and apply. So we already created our quantum circuit. We're just gonna apply these functions here to the circuit we've already created. We already have a QC created here. We just created. So the only thing we're gonna do, we're gonna apply a Z gate here. That's gonna read in C1. Simple. And if, oh, sorry, it's gonna apply the Z gate if C1 reads 1. Sorry, so we're gonna apply if. That's why we apply the C gate, but we add an extension if. If C1 reads 1, it's gonna apply the Z gate. It's just teaching us how the command works. It's just a practice to make us understand how the gate if works. So you write first the gate you want to apply and the condition you want to have. See if is the condition. If classical register reads 1, I will apply gate Z to qubit 2. Okay. To change which gate I'm applying, I can just change the number of the register. If you look here, we just changed where we are applying the Z gate. I'm applying to 1 here instead of 2. If I want to apply to 0, I just change it here. Okay, it's rerunning. That's why it's applying twice. If I want to apply only once, I need to clean. Can't do it here. I need to clear. And I can run it again. Okay. Okay, so let's go back there. Okay, now I'm showing that I'm applying the Z gate to Q0. It's just playing around. You should do by yourself. You guys should do by yourselves. Try and see what happens if you change and play with things around. So now it's gonna be a real teleportation. Let's try to do it carefully to not confuse. In this experiment, we are going to imagine we have two people, Alice and Bob. Alice has a state psi that she wants to send to Bob. Alice has qubit 0 and Bob has qubit Q2. Using teleportation, we can show the state psi transferring from qubit 0 to qubit 2, Q2, on the same circuit. Unlike a swap operation, Q2 and Q0 never have a quantum gate connecting them. The only information transferred are two classical bits, C0 and C1 registers. In order to teleport state psi, we must create an entangled pair of qubits and give one of them to Alice and the other to Bob. One piece of entangled to Alice and the other piece of the state to Bob. In the experiment, we can imagine a third person, Charlie, creating the entangled part to each of Alice and Bob. This is going to be the qubit Q1 and Q2. So in the lecture on Sunday, the lecturer, the person giving the lecture, she didn't mention Charlie because in her hypothetical situation, Alice and Bob meet somewhere and they create together. In some illustrations of the quantum teleportation, we have this third person, can be Charlie, sometimes it's called Teleron, has multiple names, giving the entangled state. It doesn't matter, it's just a figure. The important part is that Alice and Bob share entangled state. It's gonna be a Bell pair, okay? So Alice starts with Q0. Charlie creates an entangled pair, Q1 and Q2. Charlie then distributes Q1 to Alice and Q2 to Bob. In order for Alice to send a state psi of Q0, she only needs to send two classical bits of data to Bob, and Bob will be able to completely recreate psi on his Q2. Amazing. But there's two more key parts that we need to figure out. At least Alice needs to know what two classical bits to send to Bob, and Bob needs to know how to interpret those classical bits as instructions to recreate psi. So let's see. Let's first define a function that creates our abstracted teleportation protocol. We've done this for you. When reading through this function, you may notice an unusual gate being applied called snapshot. This gate allows us to save the current value of the state vector to any stage of the circuit. It is only allowed to be used when simulating with state vector simulator. This is because state vector simulator is simulating the experiment by calculating probabilities at each point of the circuit. As it is, a simulation does not involve any real qubits. Recording and therefore measuring does not alter the state of the qubits. So when using state vector simulator, you're just doing math with your circuit, just like when I did this drawing or the other one I was showing before. It's okay to measure, but in a real quantum computer, if you measure, you're gonna collapse the state, so you cannot measure before finishing everything. Otherwise, it's gonna be very confusing. It's gonna be all messed up. Okay, you're gonna collapse the states because they have probabilities to be found. So if I measure here, I have 50% chance to find 0, 0 and 1, 1. And if I measure it here in a real quantum computer, I'm gonna transfer only one of those. I'm gonna be applying only one of those to psi, and it's gonna be all wrong. So in a real quantum computer, this doesn't happen. We can only do this here because we're gonna use a state vector simulator just to show how it works. So this is how the function will look like. We will have a function called teleportation circuit, and it has one argument that's psi, okay? We will see this step by step, but let's look through it as a whole now. We're gonna initiate the state psi. This is the command we use to introduce to our quantum circuit the state psi. We need to use this initialize command as it's shown here. We're gonna give the name init gauge, and we're gonna call it secret message. And then we will create our circuit. And we already did it here. We know how to do it here because we created it here. This part here before measuring, we created it here. So we're gonna just be using it here. So we already know how it works. We will have 3 quantum registers. They're gonna be Q0, Q1, and Q2. And I have 2 classical registers. They're gonna be C0 and C1. And our quantum circuit is gonna consist of a quantum register that has 3 parts, and C0 and C1. And we will have several steps here after that. We're gonna append to our circuit the init gate to qubit 0. That's how append function works. This means I'm putting my initial state to my circuit. I'm gonna do this first part here when I do the append. I'm gonna put a quantum barrier just for statistical reasons. It doesn't do anything to the circuit. It's just like to separate the states. And then, because in the end we're gonna be simulating and comparing, we're gonna take a snapshot here just to be how do you say didactic, just to explain things. We're gonna take a snapshot here, okay? Just because we're gonna use state vector, we're gonna understand it better later. And I'm adding another barrier here. It's just not necessary, it's just statical. Now, we will see how to create a function with these arguments here. It's gonna be creating a Bell pair. You're gonna see it soon. But we already know because we saw last week how to create a Bell pair, but we're gonna do it again. We have another little function inside the function here. It's called Alice gates. They have 3 arguments. We're gonna see soon. We have this little function here, measure and send. We have Bob gates. And we're gonna, in the end of everything, take another snapshot because we will compare. So let's do calmly now. We know that we will be using this Bell pair here. So we're gonna create first this Bell pair, the phi plus Bell pair. And we know also from the classes and from our math here that depending on the classical bits I read, Bob will need to perform some operations. So it's just telling you here what's gonna happen, what you need to do, what Bob's need to do when he measures his stage. So it's very, very well explained here, step by step. It's nearly zero work with just following what instructions say. So we saw that inside here, inside this function, we have create bell pair. So that's what we're doing. And how? We're creating a function with 3 arguments. That's the quantum circuit A and B. Following the instructions, replacing a Hadamard gate in A and a C naught going from A to B using A as control and B as target. So this is the function we create that's gonna work here. And Python works in such a way that if you already have the function with the arguments you want, you are going to need only to define what are the values of the arguments. In this case, A is going to be qubit 1 and B is going to be qubit 2. So that's why we're creating here with only A and B, because Python is smart enough to know that when I create a function, I put these arguments here, these names here, and I just need to define here when I call the function. So I'm calling the function and saying where I want the function applied. Okay. So next step is creating Alice gates. We remember here to, this was the bell pair, the first one. Now we need to create the Alice gates, and Alice needs to apply a C naught with Q0 as control and Q1 as target. And after that, a Hadamard gate in Q0. So that's what we're doing here. We are defining a function that when I tell what's A and what's B, I'm applying a C naught with A as control and B as target. And I'm applying a Hadamard gate to A. Okay, I don't need to draw here. That's when I was testing. It's no need to draw. I'm gonna mute this. Okay, so I need to create this function, and when I call this function, I'm applying it to 0 and 1. I'm calling A0 and B1 now. Okay. Now we need to create the measure and send function. So as the instructions say, it's asking us to send wherever it's A to classical register 0 and wherever it's B to 1. So that's what we're doing here. This is measure and send function. I'm just writing here. And when I call it here in my main function, I'm calling from 0 and 1. Okay. And now Bob gates. Bob gates are going to be conditional ones. If the qubit I say, if the qubit, if the classical register is 1, reads 1, I'm going to apply the X gauge to the qubit I say. And I know it's going to be qubit 2, but we're going to call the function in the circuit. And the same for gate Z. If the classical register that I'm assigning to Z reads 1, I'm going to apply Z to the qubit I say, and I know it's going to be 2. And that's what I'm doing here. I'm in the function, I'm substituting qubit by 2 because I know it's going to read from 2. And my CRX and CRZ are going to be C0 and C1. That's how I call the function. I'm going to take another snapshot and I'm going to return. So now that I have every function done here, I can draw the circuit. And I'm going to just run this. I'm going to run all my functions. And I'm gonna call now With this state psi that was pre-prepared, it's a real state because the amplitudes, when you square them and you sum them, it gives 1. With this pre-prepared state, I'm gonna call the function I just created, doing all the little functions inside it. I'm gonna call this big function here, just calling the name and having psi defined, okay? So how I call the function? I just need to write it because I have psi, I have teleportation circuit function, and I just need to make it run. So if I run it, there it is. We in the beginning labeled it a secret message when we appended. We said it was going to be psi. We see here clearly we have the creation of the bell pair. We see here the Alice gates. We can see here the measurements we're doing. Q0 is reading, being read in classical register 0. Q2 is being read in classical register 1. And the if things, if classical register 1 reads 1, we apply X. If classical register 0 reads 1, we apply Z. And just let's remember that we read Q1 and Q0. Can you guys see my whiteboard? I hope you guys can see it.
Yep, we can.
Okay. You see me drawing blue here?
Yes.
Okay, cool. I was so scared I was not showing it. This reads in classical like this, okay? The order changes, just to not confuse, okay? It's very important to have it in mind, to not confuse. So that's why when you have 0, 1 here, you read in classical like this, okay? Because I'm reading 0 in classical register 0, and I'm reading 1 in classical register 1. Okay, it's important to remember because it causes confusion. It was a confusion for me when I was learning. So that's it. That's our quantum teleportation circuit. That's how we made it. We did a bunch of little functions that fed our big function. And in the end, we have only a simple line to call teleportation circuit. And that's our circuit. That's the thing we draw here before in the beginning. That's the big math thing we draw here in the beginning. We got to these conclusions. It's all clean, much better than my writing. Smooth lines, all clean, very well explained by Python and QxQ. So now,
can you increase the size of your font a little?
Sorry, what?
Can you increase the font size? Like, I mean,
zoom in a bit.
Just a little more. Thanks. Thank you.
This?
Yeah, that helps. Thank you very much. Appreciate
that. Okay. So yeah, can you see the circuit now?
It's fantastic.
Okay, cool. Good. So you see here, secret message, very little here. It's hard even for me to read, but what's reading here in the purple label is this psi state here, okay? And here we have the bell pair, we have the gates Alice applied, we have the measurement, we have the if gates, the function, fantastic. Now we're gonna run the circuit, we're gonna run the simulation. You're gonna use state vector.
I'm sorry, can you just scroll down a little up, please, for the circuit diagram? Yeah, here we are doing a measurement. Should it not be after applying the X gate and Z gate?
We are applying the X gate in QxQ if we read classical register 1 as 1. And we're going to be applying the Z gate to QxQ if I read classical register 0 as 1.
No, my question is the moment I do a measurement, the state will die. So then Is
Yeah.
this the right position, or I have to do it after
Yeah.
applying?
Yeah,
the gate?
because, yeah. Okay, what happens in quantum teleportation is at the moment Bob measures the state, he collapses it. He measured, boom. So the moment Bob measures something here, he will measure either 0, 0, 0, 1, 1, 0, or 1, 1. Okay, that's why we measure it before. At the moment he measures, let's say he measured 0, 1, he killed the other ones, he collapsed the function in this state here.
Right.
Okay, so he knows he has 0, 1. So he needs some sort of classical communication with Alice
Okay.
to know.
Understood. 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 Thank you.
Welcome. So when he collapsed, he needed to tell Alice, hey, or somehow Alice has sent an envelope to him saying, hey, that's all you're gonna do. Somehow there's a communication or telephone call, something. It's gonna be telling him, yes, when you measure, when you collapse it in 0, 1, that's the operation you're gonna do. So that's what the circuit's showing here. And it's like the moment I understood it, I thought it's so fantastic that I told my husband, I'm so ashamed it wasn't me finding it. I wish so much it was me finding it because it's so beautiful. I don't get sick of looking at it and redoing the calculations because it's so fantastic. So why did we use the snapshots before? We use them because now we're gonna run the state vector simulation and we're gonna read states and we're gonna compare states to know if it worked. It's a test if our circuit works. So we're gonna run the simulation. We're gonna read nothing here because I'm not asking to come back with anything, but I know the snapshot I took, the first snapshot I took in the very beginning of the circuit, the first snapshot was here. I took it here. I know I'm reading Alice state. And again, I'm not collapsing it at this moment because it's just math. State vector simulator is just math. It's not a real quantum computer, okay? It's a math simulation. So it's okay to take a snapshot here. So that's why it works in this situation. It's a snapshot, it's not even a measurement gate, it's just a snapshot. It's like taking a picture. And in the end, I'm taking a picture of what Bob measured in the very end after he did everything. Even after X and Z, I'm doing another snapshot here. And I'm gonna compare these two. And that's how we compare. We defined another function. It's just for completion because like just from visual inspection, we know it works. But as we are in Python, as we're doing it, why not? We just go a bit further and check it because Python lets us do that. And the person developing the homework had this work to show you, so you should try it. So let's try to understand. We made this small function called check same state. A has Alice, Bob, and Cy as parameters. I'm gonna call a string, and I'm gonna start this string, and it's gonna be Alice 0, and it's just the way Python works. Let's keep going to try to understand it better. And I'm calling another string B, and that's how Python works again. If we just try to start B here as B equals Bob 0, it's gonna bug. You can try by yourself, but it's not gonna work because Python doesn't work like that, because the order we have the arguments here, when we call a second string and we want to start a second string, we need to do like that. C for C in Bob 0, and this C is this argument inside here. If C is different from 0, it's just the way Python works. You can just trust it at this moment. Of course, you're free to explore and go to forums and see why. But at this moment, I can tell you it's how Python works, and you're gonna trust it to keep going. So what we're gonna print in the end with this function? We're gonna print size state and size 0. And 0 and 1 here, it means just the position of the elements in this string. This first thing here is the box 0, and the second thing here is the box 1 that he's calling here. Here, 0 is just the first part of the stage, and 1 is the second part of the stage. Okay? I'm gonna call just this phrase Alice's state. This is just a label. I can print whatever I like. I can print storm and sunny. I can print whatever I like here. It's just for like making it consistent. A0 and A1. And I know that here, let me show this is important too. I recorded my snapshots in this list here. And I know snapshot 1 is Alice stage. And I know snapshot 2 is Bob stage. That's why when I call this checksum state function here, I already have Alice because it's Alice stage here. Okay. I know it from this line here because I recorded it here. So calling Alice 0, I'm calling for short A0, A1, because these are the arguments of the function. I'm going B1 and B2. So now let's see, when we read in the beginning, Alice's state was the size stage. So Alice state and size state should be the same. A0 and A1 should read exactly like this. A0 and A1, because it's the same as size stage. And to know if this worked, B0 and B1 should read the same too. Just the way the person who made the homework decided to run this function, and it's a great way of comparison, he just summed up the coefficients A1 and A0, and they round by the 5 first numbers. It's rounded. And if it's equal to the sum of the elements in B stage, so it means the state was teleported, because if the sum is equal, it means it is the same stage. Otherwise, the state wasn't teleported. And now I'm gonna use the function. And now, remember I said I know Alice state and Bob state. These are the arguments here in this function. And we know we have Alice state and Bob state. These are the things I'm calling here. So when I run this function, I see that the state was successfully teleported. If we look at size stage and the numbers we have here, the numbers we have here and the numbers we have here, we see exactly the same state. So it works. It's fantastic. It works. It's done. Success. So also as a challenge and as further work, they suggest us to try changing size and see if it still works. So I already wrote it here. I'm gonna go to the beginning here just to show you guys. I already prepared it here. Another size state that still works. And to prepare this next stage, what I did, I just took sine and cosine of pi over 4. And I wrote these states because I know square of sine plus square of cosine is 1. So I just took the sine and cosine of pi over 4 and brought here to create a state which the squared sum of the amplitudes is the probability is 1. So I prepared another state, and I'm gonna run the function with this state, and it should work, okay? And I'm running everything. Oh, if you see here, my secret message is tiny, but it's the new state I wrote. I'm gonna compare them. And now it's my new size and success. See my new size stage, and Alice should be the same, and Bob, it's the same. Okay, so cool. It works. It's fantastic. You guys should try by yourselves. If you try a stage that doesn't give the probability 1, it's not gonna work. Okay, it's gonna bug. It's gonna tell you it's not a stage. It needs to be a stage that the square sum gives 1, because probabilities should be summed up. The amplitude should be squared and summed up to give 1. So try it with other things and try to see. Now another thing he says here, how would you expand this circuit to send more than one state to Bob? So my solution to this problem, the way I did, I just went to my function. You guys can try by yourselves. I just went to the function, and instead of using 3 quantum register, I'm gonna zoom it up to be able to show. I did 6 quantum
Zoom a
registers.
little more, ma'am. Can you zoom it a little more?
Yeah, I just added some things. The functions were ready. The small functions were all ready. So I just added more quantum registers and more classical registers. And I called the functions now for the second part of the circuit. Now you need to pay attention what you're reading, where you're creating your bell pairs, where you're creating your gates, where you're measuring sending, where you're creating your Bob gates. And I took snapshots in the same positions. So in the end, when I run the function, see, I had a secret message and a secret message too. So I just recreated the same circuit here, and I just added. So I don't know how quantum computation is gonna be in the future, how other problems are gonna be sorted out, but that was my solution to it. Like, as I say, it's such a new field. If you guys have any ideas, anyone who becomes a researcher in this field and finds smarter ways to do the calculation, to find gates, to write circuits, even that has the ideas how to implement it, is gonna be very successful, because it's such a new area. There's so much to find and to discover, and it's a very exciting area to do. Let me see, there was another thing I wanted to say. I'm not sure if I said it all, but yeah, let's go to the homework. If I remember, I will say. Okay, but I hope this is very clear to you guys. And the only way
I had a question.
Yes, hey.
I just, I think it's part of activity 3 where you have B equals C for C, Bob, bracket 0. Can you clarify what the C for C means?
Can you see my screen? Are you seeing?
I can.
Yeah,
thank you.
C4C here. Yeah.
Yes, that line.
It's the way Python works. It's the logics of computation. I can try to bug it for you so you see that doesn't work. If, for example, I change Bob, I will bug it intentionally. That's the way I understood it, okay? I'll bug it intentionally. If I put Bob here in the beginning and I try to run it, it gives an error message because it bugs the system. So when Python indexes things, it indexes like taking into account the order of arguments you're placing and the order of the elements inside the string. So the way it does, you cannot only just call like B0 again or Bob 0 again, because it's gonna bug as I showed. Like I can do it too, just to prove. I'm gonna bug it again too, here with this. And then I will go for that. This bugs too. It gives an error message. Okay, so Python indexes things by starting it over and say, it doesn't need to be C, can be E for E, and it will work the same. It's just that you don't need to say the name of the variable who is inside here to say you're calling it. It knows enough that if I'm calling it 0 here, and if I say E, now I'm changing, E is different from 0, it knows I'm talking about the element inside it, because I'm saying E for E in Bob. If E is different from 0, when I say E is different from 0, I'm defining that E is a number and should start after 0. I know that E is inside this variable Bob, and I'm doing it for each E that is in Bob 0. So that's the best way I can explain it to you, is the way Python indexes things. And you can call it anything you want. You can give any letter you want and it should work. Okay. That's just the way Python works. I advise you, if you're very curious, to go to forums and ask. Maybe someone has better words to explain. So if I keep just reaffirming with the same words, I'm not gonna give you any improvement, but you should try to go to a forum and ask why Python indexes it like that, okay?
Okay. Yeah, thank you for your help.
Welcome. I'm sorry if I'm not very clear, but that's the best way, because that's how I understood to myself. It might not be the best way for you to understand.
Excuse me, may I ask you something?
Yeah.
Where could we find the recordings of the previous homework sessions?
You'll find it on Canvas.
The recordings of the homework sessions.
Yeah, exactly. You go to Canvas, you go to modules, and you're gonna find homework in Canvas. I'm gonna show you. In Canvas, you go modules, resources, after like each week, like for example, homework, week 16, you find homework review section. See it here?
Yes, I see.
Yeah, if you
Thank you.
click here, you're gonna have the link, okay? Welcome. So for all homework sections, you have it there. So let's
Okay, thank you very much.
Welcome. Let's try to do the questions in the homework and see if all the questions arise, because we have a limited time and we need to finish this. So if there's more time in the end, I can answer more questions. I'll try it. So in quantum teleportation, if Bob receives the classical bit pair 0, 1, what gate combination should Bob apply to this circuit? And if you guys remember when we did classical, he is receiving 0, 1. So it should be X. So Letter C should be C, X gauge, if he reads the beat, classical beat pair 0, 1. Question 2. Qiskit allows us to use a function called snapshot while running the state vector simulator to look.
What was the first answer again?
Letter C, X gauge. Because it's the classical beat pair 0, 1, and we have 0, 1, you apply X gauge.
Z gate, that's why I just wanted to clarify.
No, it's X gauge because it's the classical. Yeah. Okay, to not confuse classical register with quantum register. So it's very easy, and I myself confused, got myself all messed up because sometimes I'm reading the quantum. It's not the quantum, it's saying it's reading the classic, and the classic 0, 1 corresponds to the quantum 1, 0, okay? So it's classic 0, 1, X gauge, then X gauge. Okay, so talking about snapshots, I talked about it when we're doing our circuit. For simulating quantum teleportation, we can use state vector simulator snapshots to look at the quantum state during the protocol. Why is this impossible to do on real quantum device? So it's not because we haven't solved the electron snapshot conjecture. It's not because it's too expensive to build a snapshot machine, because the snapshot machine would be, I don't know, a camera taking a picture. And it's not because there's so much noise involving taking snapshots. It's because a snapshot involves a measurement of quantum states which would destroy the entangled pair. So a snapshot is a type of measurement. Any type of measurement destroys the entangled pair. That's why. Okay, so it's B. Okay. What does the no cloning theorem prevent us from doing? Oh, now I remember what I wanted to say that I forgot. Okay, I'll say now. As a reminder, the no cloning theorem states that it is impossible to create an independent and identical copy of an arbitrary unknown quantum state. The non-cloning theorem says it's possible to do Control X, Control V, but not Control V, Control C. Okay, when you do Control X, you don't see the thing anymore, and then you do Control V, you see it again. When you do Control V, the copy is still there and you can copy it. But in the quantum world, you don't have two identical states coexisting. So
can you repeat that answer again for number 3?
Yeah, I'm just saying, I'm just making a comparison that like in the quantum world, you have Control X, Control V, but you don't have Control V, Control C, Control V. You have Control X, Control V. You can cut and find it somewhere else. You cannot copy. It's like you have Control X, you don't have Control C, okay? You have copy. You have cut, you don't have copy. So two quantum states identical cannot coexist. For a copy to exist, the original needs to be destroyed. So that gives us the answer. I don't think I need to say because I just said. So you guys figured because I just said it. Okay. And yeah, that's what I wanted to say. I want to make it sure that you guys understand that you cannot have it two quantum states coexisting. So what is the role of the third person, Charlie, in the first step of quantum teleportation and superdense coding? Charlie refers to the person mentioned in Fran's lecture in this week's lab. During the lab, not everyone had the same structure. My instruction made it clear. I hope every structure made it clear. that Charlie, sometimes in some illustrations of teleportation circuits, Alice and Bob don't create together. They have a third person that gives them the entangled pair. Okay, so I pretty much answered the question. The third person gives the pair. Instead of Alice and Bob meeting and making the pair themselves, a third person gives. It's just an illustration. In some configurations, in some illustrations, you have someone called Teleron. Sometimes it's Charlie. Sometimes it's whoever. It's a common friend that they have that gives them, or common enemy, who knows. But the third person. So I just answered. I don't need to say which letter because I just answered.
Wait, I don't get that part.
Okay, so
Part 4.
you know when you have the quantum circuit, the first bit, let me move it a bit. Can you see my quantum circuit here?
Yes.
Okay. So you know here, this first Bell pair, in some illustrations of the quantum teleportation, it's just a way you tell a story. Alice and Bob meet somewhere in the world. Let's say they meet in America, they meet in the United States, and they together build this pair. In some illustrations of the same story, instead of them meeting, someone they know somehow got to give them a bit of state to Bob and a bit of the state to Alice. So Charlie, in this second way to tell the story, is the person who provides this Bell pair, because they need, in order of teleportation, super dense coding to happen, you need to have an entangled pair. That's how they communicate. Quantum communicate is having an entangled pair. So Charlie is this provider. So I just said Charlie is the provider of the entangled pair. Okay. So yeah, this leads us to the last question. So imagine Alice wants to send a 1,000-character document to Bob. Alice and Bob also happen to have 2,500 shared entangled states between them. Okay, because Charlie, or let's say Charlie the provider, let's use this figure. He can give, instead of only one, he can give a bunch of entangled pairs, as much as they like. They can receive like 1,000,000 of entangled pairs to play around afterwards. It doesn't need to be only one. At the moment they receive the pairs, they can receive a bunch. Okay, because whenever you transmit, you destroy the entangled pair. So you need, for each operation, you need a new pair. So they happen to have these many states, entangled states. Assuming that each character can take one of the 32 different character values. So imagine that you have 32 possible characters, and that we are only able to send one qubit at a time. Okay? How many classic bits would you need to send the document? Now, using superdense coding, what's the minimum number of qubits required to send a document? So let's do it. Okay. You have 0. I'm going to change this color here. You have 0 or 1 as possible bits. So we have 2 possible bits. And we know we have in total 32 characters. How much I need to elevate 2 to have 32 characters? In other words, I know when I have a quantum qubit. I have these slots. How many slots I need to be able to write 32 in binomial? That's basically the question. How many slots I need here? So how much is this x? So if I do log base 2 of 32, I can find x. But it's such a simple answer that we know just to be used to do with binomial. I know this x is gonna be 5. So I will need 2, 3, 4, 5 at each time to send. For each character, we need 5 slots here. So x equals 5. So now I know the text length is 1,000 characters. So in the end, I will need 5 times 1,000. It's going to be 5,000. So 5,000 classical bits. That's how much I need. But how many quantum bits? So we know from superdense coding that we need 2 classical bits for each quantum bit. So to get to this answer, I just need to divide this. It happens to be the amount of qubits they have. So I need 5,000 classical bits for 2,500 quantum bits. So yeah, I'm just gonna do it different here to not confuse. Just gonna erase it here just to say how many slots you need. Just to not confuse because these are classical. Okay. So that's it. It's 5,000 classical bits for 2,500 quantum bits.
Also, what was the answer to question 2? I didn't quite catch that.
The question what?
2.
2. Why is it impossible to do on real quantum device the snapshots? I don't know how much you followed, but a snapshot is a measurement. And you know from quantum knowledge, whenever you measure a quantum thing, you collapse the state. So if I have a state that's is I know when I measure, I have 50% chance to find 0, 0 and 50% chance to find 1, 1. At the moment I measure, like if I measure 1, 1, I kill 0, 0. So I only have 1. So what happens? This is in the real quantum world. In a simulation or in the mathematical world, I can still see the probabilities, I can still manipulate them. And the state vector simulator, it's just doing mathematics on your system. So in a real quantum measurement, you would collapse and destroy the other possibilities. But with the state vector, you can take a snapshot, you can measure without destroying, because it's not exactly a quantum computer, it's just a simulation of the mathematical, it's the mathematical trick you're doing. That's why. So it's because a snapshot involves the measurement of a quantum state. Okay, did you understand?
Can you repeat question number 5, the explanation, please?
Okay.
Sorry about that.
No, it's fine. Question 5 is about how many
Exactly.
how many qubits you need. Okay. Let's see again. So I said there are 2 possible. I'm gonna do it blue now. 2 possibilities to write on each slot. That's 0 or 1. And the classical, I can understand that how many slots I need to write 32 in binomial, or binary, sorry, in binary. So 2 elevated to how much makes 32? So the mathematical operation is log the base 2, logarithm the base is 2 of 32 gives me x. But it's such an easy number to remember because we're so used to it. We know we need 5 in order to write from 1 to 32 in binary numbers. We need 5 slots. 3, 4, 5. We need 5. Okay, it's 32 characters. That's why I have 32 here, because the possibilities of writing, you can write A as 00001 and B 0000010 and so on. So I have 32 characters and 32 possible ways to write the characters. And I need five slots for it. But also I know that the length of my text is 1,000 characters. So I'm just gonna multiply how many slots I need for each character, but by how big my text is. And it's 5 times 1,000, it's 5,000. 5,000 classical bits. That's how much I need. But from super dense coding, that's what he's asking here. We know that for each 2 classical bits, I need 1 quantum bit. So I'm gonna divide it by 2. And then I'm finding 2,500.
Thank you very much. It's very clear now. Thank you.
Okay, cool.
Very
Glad
clear.
to know. Glad to know. So yeah, so I have some minutes more for any other question. If you guys have any other question, or if you didn't understand at all, it's the time to complain, say I'm not understanding.
So even for this particular homework, we're gonna upload the Jupyter notebook and then do the analysis on QxQ as you did for us today, right? You showed us today.
So sorry, can you say again? I didn't.
See, even for this homework, even though the homework is kind of a little easy, we're gonna take the Jupyter notebook, import it into the QxQ and go through this whole programming exercise, right? Just to get a good feel for it.
Oh, okay. Good.
I'm happy to
Good
help
that-
with this one. Just Amar, this quantum teleportation and superdense coding are really complicated from a coding perspective, and so we didn't want to like quiz students on the homework on exactly the code. So you can answer the questions like Gisele just did with a conceptual understanding, and so it's kind of optional if you want to practice the code.
Yeah.
Sure. Ma'am, I just want to make one more extra comment if you don't mind. You folks are doing a wonderful job. I even sent you a New Year's card. I don't know whether you received it or not. At your address in California a while ago. But
Yes,
you folks are
that
doing
was you. Yes, we did receive it, and our whole team passed it around.
And one more small comment I would like to make, ma'am. This is done very sincerely. Of course, I'm not very smart. I'm a stupid guy. I did my chemical engineering graduate work at Madison, and I'm also from IT like Akshay a long time ago. But next semester, whenever you're teaching the class and you want somebody free, I don't want to charge anything, free. Of course, I can never measure up to what teacher is teaching us today. I'd be more than happy to volunteer. I really mean it. Okay, I'm more than happy to volunteer. I'll send you my contact information, and I'll do it free as long as you want. I don't need any money for this.
I'm a
Because I
volunteer.
can never match Madam Gazelle, my teacher, with you. Okay?
I'm doing for pleasure here. I'm volunteering too.
Yeah, I know you're volunteering, but I like to do that too, ma'am. Okay, thank you very
Okay.
much.
Okay. Good to know.
You folks are doing a wonderful job. I could never teach like you, believe me.
Thank you.
And I've taught before too, but still, no way. Have a good weekend, all of you. Okay.
Yeah, you guys too. So If any other questions, any other doubts, complaints.
Sorry, I have a question.
Yeah.
I want to know what is the difference between the snapshot and the barrier, because I see in the circuit that the representation is the same.
Yeah, well, the measurement is an actual gauge you put in the circuit. Okay, this is a measurement. A snapshot is a type of measurement that's not a gauge. It's like I'm taking a picture or I'm recording how the circuit looked like at this moment. So it's like I'm taking a picture. It's like I am telling you, see, in the beginning, the state was like that. Take note, take note. So you're gonna write it up. So I'm gonna play around, and in the end, after the real measurements and everything, I'm gonna tell you, take note again. That's
Okay.
the option snapshot. That's how snapshots work. It's like I'm copying the information I have. So because there's no real quantum state copy, this is just an artifact we use to understand, okay? Because if you measure, you kill the state. So it's a type of measurement, but not a gauge.
Okay, I understand that, but the barrier, I
The
don't
barrier,
know.
yeah.
What is doing that in the
Nothing.
circuit? Nothing?
Nothing. If I remove the barriers, it's gonna work the same. It's just a trick to make it look cuter. If I remove the barrier, I'm gonna try to do it here. If it doesn't bug for other reasons, I'm gonna remove some barriers for it. I'm just gonna mute it here instead of deleting. You can play around in your computer too. Don't be scared of playing and trying, but it should work the same if I remove barriers. Where's my circuit? See, I removed barriers. It's the same. It's just because when you put the barrier, it makes easier to understand. Otherwise, they get so mixed up here that you do not understand. So it's a good thing to put the barriers, because otherwise it's gonna be this mess here. I'm still doing the operations in the correct order, but your secret's gonna look so messy that you will get lost. So you want to add barriers to make it look better. Okay?
Okay, thank you very much.
Welcome. Any other questions?
Thank you, and have a good weekend.
Okay, thank you. So I'm gonna wrap up and I'm gonna
Bye-bye.
say have a good weekend. So feel free to use Piazza to ask questions. Phil, the guy that creates the homeworks, he's super smart, intelligent, and he's always there answering questions. He's doing a great job answering. So any doubts you guys should ask in Piazza. And it's also good to interact with other students, okay?
What's his name, man? What's his name?
Oh, the guy who creates the homework, I just know it's Phil. I know because he shows in Piazza.
Okay, thank you.
Welcome. Whenever you ask a question, like when you have instruction, it's usually Phil or one of these structures. And so I know that he creates homework sometimes. So
Okay, thank you.
okay.
Bye.
Welcome. So good weekend, everyone. Yeah, and I guess see you guys next week.
Thank you, Gisele. Bye, everyone.
Bye.
Bye.
Bye. See you.
Bye-bye. Thank you.
Bye.